I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for this opportunity we have just to meet together for the students and just the freedom we have just to talk about you openly. Just pray you help us to understand what we cover here today in algebraic topology, and that you be glorified, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so we have finally reached chapter 7, and so chapter 7 is on simplicial complexes. I better figure out that. Complexes. But then I want to say complexes. I don't know. This is complexes, though. So anyway, simplicial complexes. And basically, this is where we start to get some concrete, terminology. Well, I would say so how you actually calculate anything in what we've been doing. I mean, we have had definition after definition after definition after definition after theorem after theorem after theorem, and it seems like calculations are few and far between, right? I mean, everything we have calculated has been something very, very special, really, right? Sphere, point, all of Rn, various twists and combinations of those things. This chapter, the simplicial complex, gives you a tool to start gathering topological data about things that are a little bit more interesting. And a lot of this I think we have more or less covered in the advanced calculus class, but at a different level of rigor, generality. And I don't think we always didn't. I'm trying to remember, did we always use triangulations in there? Didn't you have it set up with, where am I thinking? Someplace they had it set up with rectangles rather than triangles. Where was that?
That might have been in
that wasn't advanced?
That might have been in differential geometry.
Is that O'Neill? O'Neill's differential geometry does rectangular? I don't know. Rectangularizations are fun. For me, they're much more natural than triangularizations. But anyway, this is a pretty, we're very triangle-centered in here, I suppose. Anyway, so here's the definition. What was I just saying about just definitions and hardly any calculations? So I don't want. I mean, you're so used to that. I don't want to really shake you from it. So
Gotta
see here.
ease out of it.
What's that?
We need to ease out of it.
You need to what?
Ease out of it.
Oh yeah, we're gonna really take our time easing out of it. Let's see here. VQ is a Q simplex. What's that mean? He says, in contrast to the singular theory, Q simplex again will once be again an honest space, and not a dreadful continuous. He didn't put dreadful, but a continuous map with domain delta Q. Excuse me. This is actually a Q simplex. So what did that? I think we defined that earlier. Where was that?
It's just the affine combinations of those points in Euclidean space, right?
Okay, so it's the affine.
Or I guess not affine, but the
Convex.
right.
Convex full of those points. Okay. So this is a Q simplex, and we denoted the vertex set. So basically, we're going to come back to that earlier discussion of concrete simplices, and we're going to add a little bit more to it, and then we're going to eventually talk about how to do homology with this stuff. This is the so-called simplicial homology eventually. But first we have to build up the simplicial complex, obviously. So there's its vertex set. Definition, if S is a simplex, a face of S is a simplex S prime, where the vert of S prime is a subset of vert S. So let's see here. Basically, S prime is face. It's a face of S with. I'm sorry. I'm sorry. S prime. Words. Ugh. Grief. It's not complicated. So what is it? What is a face? If S prime is a simplex and curses. I keep forgetting. I just need that the vertices of S prime are a subset of the vertices of S. Oh, right. I was thinking I also needed S prime was like a subset of S, but that's not necessary, right? To say simplex, it means it's like you were saying a convex hull, right? So it's like it's in some sense S prime is already a subset, if you think about it. The vert of S prime is a subset of vert S. And then what's a proper? He also defines a proper face is what?
When it's not there.
Right, so this add the not equal gives proper, right? Alright, so definition, a finite simplicial complex is a finite collection of simplices in some Euclidean space, right? So simplicial complex, finite. That makes you wonder, doesn't it? How would you define an infinite simplicial complex? Need some notion of convergence or something, right? Anyway, so a finite simplicial complex is a finite collection of simplices in some Euclidean space. Such that what? If S is a simplex in the simplicial complex K, then every face of S also belongs to K. So it's it's got all the faces for each simplex which is in it. And two, if we have two things, if we have S and T in the simplicial complex, then the intersection of these simplices, S intersect T, is either empty or a common face of S and T. Alright, so this definition, he's got more to say here, but I'm going to jump ahead to his little example because I think it's important to do it now. So he gives this example down here. Here's like, if you look at ACB, and then the blue is the blue triangle, D, E, F. So this is your S, this is your T. If you look at S and S and T, right, and their faces, right, if you look at ST and the faces of S and T, right, it's not a simplicial complex. Because the intersection, right? And so what is a face? I mean, a vertex is a face, right? It's any subaffine piece. So if you have a k-dimensional simplex, the faces could be k-1, k-2, k-3, so forth, so on all the way down. Now here, the intersection, of course, is just the vertex D. So like D is face of T, but not S. Oh man, No, I thought it was a passive stupid cough. Seems like it's come back. Now he does mention that, well, stick with that for a second here. Now definition, if K is a simplicial complex, the underlying space so the underlying space, what is that? It's how I actually think of these stupid things. He denotes it like this. So that's actually just the point set, which all of the faces and the simplices cover. Right? In other words, specifically, it's just the union over the simplices and the simplicial complex K of S. So it's actually a subset of the Euclidean space of which we're forming this in which we're forming the simplicial complex. So in other words, it's the union of all simplexes in K. He says clearly K is a compact subspace of some Euclidean space, right? It's finite. They're all, it's a finite union of bounded things. It's obviously compact. Here's a definition then. What's a polyhedron? A topological space X is a polyhedron if there exists a simplicial complex, I guess still finite. I guess we're going to see let it be understood that all our simplicial complexes from here on out are finite. We're not going to say finite a billion times in this chapter. Simplicial, that's a technical term. A simplicial complex K and a homeomorphism H that goes from the underlying space of the complex to X. Right? Then the ordered pair K comma H is called what? Right. Now, as we've discussed some in our previous discussions of what the big picture is here, there is a special sort of universe of topological spaces which allow triangularizations. And some don't, but many, many do, certainly many interesting examples. Even ones that we can't visualize directly in terms of like three-dimensional geometry or anything, right? Like there's triangularizations of all kinds of pretty exotic spaces, so it's not that limiting. So here's his example. He says the standard 2 simplex is contained in Euclidean space R3. Define K to be the family of all vertices and one simplices of the 2 simplex. So what's the can I draw a picture? What's the 2 simplex? It's just triangle. All right. Why is he looking at it inside R3? So define K to be the family of all vertices and simplices of delta 2. Then K is a simplicial complex whose underlying space K is the perimeter of the triangle delta 2 and R3. I don't understand why he's... I'm sorry, I'm perplexed as to why he's talking about R3.
It's just for kicks.
For kicks, alright.
We've used R57.
In any event. Of course, we can draw a circle, right? That was a circle. And the point is, the homeomorphism from this to the circle, at least from the edge, the underlying space. So is it just the? Sorry, guys. Delta 2, right? What is delta 2? I guess is my question. Maybe I've forgotten.
I mean, it's kind of like the entire triangle in itself, but the K that we're looking at is just the vertices and the edges.
Okay, so he's looking at, because I was wondering, so he's looking at K as a subset of that, where that K is really just what I've drawn in black, right? Like the delta 2 in principle is all this too, right? It's also the face.
Right.
But he's saying just look at the part of delta 2, which is just the edge of it, then that's clearly homeomorphic. There's a clear homeomorphism from that to the circle. And so the edge of just the triangle, not the solid triangle, gives you a triangularization of the circle. Okay.
I just remembered why he says it's delta 2 and R3. Because you kind of like define it as like delta n and n plus 1, and Rn plus 1 is like the simplex formed by like all the, what do you call it, unit vectors, or so.
It goes back to his the epsilon I construction. You like those formulas with the epsilon i's and the the including the faces in the higher dimensions.
Right.
The
The
natural
standard
way.
n simplex is built one dimension higher than you actually would need.
Okay, thank you guys. I digress. I mean, I was hoping for something like that. Thanks, guys, for reminding us that. So, as example 2 is the family of all proper faces of an n simplex. So then there's a triangularization of Sn minus 1. So basically,
Generalizing.
yeah. So let's see here. I feel like it seems to me like delta 2 should give a triangularization of the disk, you know? And then the boundary of the disk is the circle, and the boundary of this triangularization is the simplex K we're talking about here. If that makes sense.
Maybe it does.
Yeah. He says something about the dot notation being consistent there in that next example. But beyond, of course, above this, we could think about the tetrahedron, basically. But just the faces of the tetrahedron providing a triangularization of the two sphere. All right. So, then this example is his example 3. He does a little bit more. He says that, in fact, if you look at both of this, if you look at X equal to S union T, right, as a subspace of R2, let's say,
Well,
that is.
It's the union of the underlying spaces.
Oh, I'm sorry. Good point. I was identifying the simplex with its underlying space, which is a bad habit of mine. And so that is a polyhedron. But what we have here, ST and its faces, that's not a triangle. That is not a triangularization of it. How do you get a triangularization? I mean, we need the point of intersection to appear as a face on the common simplices. So all you do is basically just cut it.
Split S into 2.
Yeah, exactly. Split S into 2. like this here, and say SU and well, let's say S1 and S2 or something like that. Right, and then like the intersection of S1 and S2 is a common face. The intersection of S2 and S2 and T is a common vertex, which is a common face. And everything that intersects has a common face because vertex is a face, and that fixes it. So anyway, all right. So there's that. Now, although he explains it in terms of he's a little bit more explicit, right? He says the K is equal to what? A, B, D. So do I need to? I maybe need to clarify something here. Why does he just list these three things? Like I thought. Maybe I don't understand the notation. Oh, sorry. No. It is as ugly as I thought. And then I just noticed, comma, and your face. No, and their faces. Okay. Okay, so yeah.
There should be some notation for that, like the closure under the face map or something. I don't know.
Like you draw like a big
Face.
over it or something. I don't know.
It's not a face, that's a hand.
I don't know why I'm thinking of this. I don't know.
Draw a face.
Face. All right.
Draw Pac-Man over it.
Like, yeah. What do you think of the face? It's a K. It's in K. No, maybe that's not a good joke. I'm working on it. I'll get the joke eventually here. Let's see here. All right. Example 4. Every Q simplex S determines a simplicial complex K, namely the family of all not necessarily proper faces of S. So basically, any simplex is a polyhedron. Okay, yeah. This is, yeah, alright, fine, whatever. Example 5. We have B, D, C, A up here. This one goes this way, this one goes this way. This one goes this way. This one goes this way. What does this picture mean? He says, consider the square I cross I with edges identified as pictured. Right? So what does that mean?
Kind of blend together. Makes a torus.
Yeah. He says a triangularization of I cross I, the insertion of the diagonal BD, may not give a triangularization of the torus because after the identification, the two distinct triangles, the two simplexes, ABD and BCD, have the same vertex set. What? I don't understand. Could you explain to me why that? This is what I don't understand. Is why isn't that a triangularization of the torus?
No, I had the same question. I was reading it earlier.
Ah, dang it.
I mean,
Most of the triangles kind of collapse, right? Or
Either S intersect T is empty, or it's a common face. Oh, we say the triangles would collapse.
maybe not. I feel like that diagonal just becomes like just like a circle around the torus. And so it doesn't really make it track, because
He does say may not. So is he saying sometimes it does? I mean, taking this, you know, basically, this is hard to do. And then, that's the tough part. Yeah, I can finally go up. So in that, I guess in the process of, I mean, these points get identified, right?
I think so.
And these points, I think, get identified.
Yeah.
oh, yeah, I think this triangularization doesn't, but like if you like did it more, it would become a triangularization of the torus. I think in this case you don't really end up with any triangles. It's just kind of like a, because like A, B, C, and D all become like the same point, right?
A, B, C, they all the same point.
And the diagonal just kind
Well,
of like
I
does
can
a
see
loop
that. I
around
can
it.
see that A and B are the same point. I can see that D and C are the same point. How do you see that these two are the same point?
Because you A, B, and D.
Oh, because we're identifying this.
Because we identify both, and so I think like it's just like one point, and then the diagonal just kind of like makes a loop around it, or something like that, and it doesn't really like make a triangularization.
So it's not actually a triangularization. It's
right,
like,
because you need like more than one point to make a triangularization.
oh, so I see. So it's not. They're not actual triangles.
Right. The next one actually does become a triangularization of the torus. So.
Yeah. So then that beastly picture he has. I think in my presentation of the differential geometry, right? Well, there I was using rectangularizations, right? So I think we get out of it there because we have.
Yeah, I think if you did a rectangularization of that, you would get one.
That's subtle. I see. So despite the appearance of triangles, it's not really that. It's, I don't know what it is. But then, so he draws this dreadful picture, right? So there, you actually have, I mean, I guess then this one, and how's it go?
Right, there's some that don't cause. Actually, maybe not.
Like, I guess this, maybe these two, maybe that too. Seems like these are all part of the same stupid triangle by if I understand this.
Right, they all kind of turn into the same triangle, I think.
But then you still got the other ones. This is intriguing. He says the minimum number of triangulation, the minimum number of triangles in a triangulation of the torus is 14. This is 18.
Let's prove it.
Let's prove it. Let's not. Let's see, this is Massey, 1967, exercise 2. I guess I need to get that book, huh? Let's see here. Now, of course, anybody who is interested in topology has seen these before, but we can also do like this. And you know, we say do like this. What do we really mean? If you want to be constructive here, what do? You start with a plane. You form an equivalence relation, you obtain these things as quotient topologies, right? By identifying points relative to some lattice or something, right? So that's how you glue things with a quotient construction. Now this, let's see here, what is that?
Is that like the Klein model?
The right one's the Klein model.
This one's Klein model?
Yeah.
Oh, I guess is the other one
Well,
real
it's a real
projective space?
Yeah, but
This is real projective space. Okay. What is it, RP2?
Hmm.
I'm not very good at seeing that one either. um, hmm. Isn't that also the Mobius strip?
the Mobius strip only has one identification.
I see. So if you just,
If you didn't have the left
if
and right
if
one,
we
or
if we just or right,
Top line.
pick your.
right.
This is the
That's
Mobius strip. So. Right. All right. So. Let's see. Where was I? Over here. So definition, let S be a Q simplex. If Q equal to 0, then the S upper, let's say S degrees, is equal to S. It's the open simplex of S, rather. On the other hand, or if Q is not equal to 0, then we define S upper circle, the interior of S, as S minus S dot, where S dot, of course, is the boundary of S. Right. So this is called an open Q simplex. Which kind of makes sense, right? So it's basically, you take your simplex and give it fuzzy edges.
Unless it's a zero simplex, then it's not actually going to be open.
Yeah.
Well, I mean, depending on your topology, but...
We hate the zero simplex. It's so weird. Oh no, I'm committing microaggressions against the... that was not even a microaggression against zero simplices. I think that was a medium-sized aggression at least. Possibly macro. I don't know. I wonder if we'll get training here soon about not committing microaggressions against students. Or how far we are away from that. Here. Hopefully far. Let's see here. Where am I?
If they're going to do that, they should at least allow students to wear shorts to class. That's like in August.
Yeah, shorts to class in August would make sense. I had some guy wear pajama shorts to one of my classes. I didn't say anything. I mean, I thought something. Dude, why? But I didn't verbalize it until now. Let's see here. Oh, okay. So observe a simplicial complex is the disjoint union of its open simplices. All right. It's plain that an open Q simplex is an open subset of S. All right. Its interior, in fact, right? But if S lies in a simplicial complex K, then the interior, S interior, may not be an open subset of the underlying space of the simplex. For example, the open 1 simplex is an open interval, but its endpoints are open 0 simplices, which are of course not open subsets of the closed 1 simplex spanned by its endpoints. This star construction is something, isn't it? Do you guys understand this?
Essentially, you're just taking the open Q simplexes that are adjacent to whatever the point is.
Mm-hmm. Let's see here. So I'll draw a token triangularization of this thingamajiggermajoo. Let's see here. Technical term. Let's see here. This is a cool triangularization, don't you think? Am I missing anything? Oh yeah, these ones. So the star of P is what you say, it's
There's 8 triangles that are around P.
it's just okay, it's just the union of all. Now is it the whole triangle or is it the open triangles? What is
That's
the
open.
so just all open so is it fair to say it's the union of all open faces which have P on its boundary?
That's what it says, essentially. That's the definition.
Okay. So for this, it is just this guy and this guy, this guy, this guy. But the does it? What about the black lines in here? Are those are also in here? Because those are faces as well. I guess my point is, so so P itself would not be in there, right? Is that fair?
Yeah, I think so.
Yeah.
So P is not there, but all of the edges are in there. However, not the endpoints of the edges. So, like, to be clear, these are gone too, right?
And I guess the edges in between aren't in there either. I don't know.
I think, but I think not this, not the joints, right? Oh, yeah. I mean,
Well, those are faces.
but not this piece here,
Oh, right.
right? If I understand it correctly. Oh man.
Because those are adjacencies to P.
Right. All right.
Okay.
Definition: if K is a simplicial complex, define its dimension. What's the definition of a simplicial complex?
So P be included. P would be included.
It's the supremum
The interior P.
of the dimensions of S such that S is in K.
Yeah, I guess P is a face, a zero face. So
Oh.
yeah, yeah. So I guess P would be included because
Oh,
P
Ah.
itself is a zero face.
I think we have just found the reason that we defined that zeroth case as we did then, is precisely what you guys said. Fill that dot right in there. But are the, I think the, but the other ones are missing. My other deletions are still gone, yeah. So the dimension of a simplex is the supremum, although that seems unnecessary since we're dealing with finite simplices. It's the maximum of the dimensions of the faces. Right. As he says, of course, a Q-simplex has dimension Q.
I mean, you've got to use the more obscure sounding terms so people will think you're smart.
Oh, well, there's no danger of that. But anyway, go on. I mean, I've already expressed my support for Trump, so. Did I really express my support for Trump? I think I've really more expressed my disdain of Hillary. That's more, I think I'm more clear on that point. What does it matter? I did tell my differential equations class earlier today. However you look at it, next Tuesday is great because we're either going to have Hillary out of the public eye or Trump out of the public eye. It's like either way it's a win. But my heart's not in it because both of them are involved in investigations which are going to be ongoing. You know?
Well, I mean,
One of them is more
if
substantial than the
Hillary
other.
wins, she'll be president, but then Trump will become a permanent Fox News pundit.
Permanent Fox News pundit.
Actually, no, isn't he planning on opening
Well, I hope
Trump
not.
TV or whatever?
Oh, I've
Did you
heard.
hear about
I've
that?
heard about that. I'm not sure if that's not just a joke. I mean, there is
I
some.
thought it was real.
There is a new conservative news network which is starting up. It's Mark Levin and a couple other people. because by now it's clear that Fox News is
Fox News.
just a sensationalist. I mean, it's the National Enquirer with slightly nicer sets or whatever. It's about to fall off. Okay, anyway. Invariance of dimension. If K and L are simplicial complexes, and if there exists a homeomorphism from the underlying space of K to the underlying space of L, then the dimension of K is equal to the dimension of L. All right. So your theorem 7.1. K, L, simplexes. If there exists F from the underlying space of K to the underlying space of L, a homeomorphism, then the dimension of K is equal to the dimension of L, so-called invariance of dimension. Let's see here. I think I need to sit down for the proof of this one. All right. So what's his argument here? He says, suppose otherwise, all right, if the dimension of K is greater than the dimension of L, and suppose they're equal to M and N respectively, it's like if you can prove it for this, then F inverse, which exists because we're assuming it's a homeomorphism, will take care of the other direction, right? So it suffices to get a contradiction in this one direction, right? No loss of generality here. Take an M simplex sigma in K, look at its interior, all right? The interior is an open set in the underlying space of K, all right? I believe that. F is a homeomorphism. We're given that. So the image of an open set is open. Sure. Seems reasonable. So there exists some P simplex tau in L. Alright, now I gotta write something down here. So we've got a P simplex tau in L such that what? Oh, and what's the inequality here? P less than or equal to N less than M. We're assuming the dimension of K equals to M. The dimension of L is equal to N for the contradiction we're doing right now. So you've got a P simplex tau in L, and what does he say? The image of sigma naught intersect the interior of tau is equal to W. And what's the deal with W? Non-empty open set. In L, I suppose, right? Well, sorry. As I've said, I'm still trying to come to terms with the fact I need to put bars around that for the underlying space. Where was I? He says for the stars, the stars of the vertices form an open cover of the underlying space of L. Huh.
Because like any face of L, it's going to be attached to some vertex, and so it's going to be, at least its interior is going to be part of the star. So I think you can, I mean, it's pretty intuitive that you can cover the whole thing with those. Since there's like a finite number, so I feel like you could work from one and just reach all of them.
Oh, okay, so I guess the f of sigma naught, right? It's got to hit something in L, I guess, right? I mean, it's a function. It's the image of a set under a function. It has to hit some points, and it might not land squarely in a simplex, but it's got to hit on one of them, right? And so then, if you intersect with the interior of that simplex, you should be left with something. And then the fact that that's, I guess the fact that he's saying that that's open because it could be looked at as a union of stars, and the stars are open sets, I guess.
Yeah.
Then what? Choose a homeomorphism of the M simplex to sigma, where the boundary of the M simplex maps to the boundary of sigma. Then U as the inverse image under phi. This homomorphism we just introduced of the inverse image of W is an open subset of the interior of delta M. And since P is less than M, there exists an embedding of the P simplex into the interior of the M open simplex, such that the image of G contains no non-empty open subsets of that. So both U and G of W are homeomorphic subsets of the interior of the M simplex. As U is open and G of W is not, this contradicts the invariance of domain theorem from the Tale of the Beast in the last chapter, right? That was the last theorem. Invariance of domain. U and V subsets of Sn having a homeomorphism. Oh no, wait a minute, was that the one? No? Well?
Yeah. They have to both be open or both be closed.
But that invariance of domain is for n spheres, right? And now we're talking about simplices. But as he says, modified by exercises 6.21 and 6.22, which I'm assuming exploit the homeomorphism. The fact that the n spheres are triangularized by the n simplex, which then means that any topological theorem you get about spheres you also have for the triangularization of spheres. Tail wagging the dog here, I think, a little bit, but where'd that go? 6.21. Bowsers. What? Oh, that's lemma. No, not lemma. I want exercise.
It's the last page.
Oh. Ah, so you can prove invariance of domain replacing Sn by Rn.
And any homomorphic space.
Oh, okay. Which is what delta n is, of course. As we talked about earlier. So difficult to show something that's so intuitively clear, right? Of course, if you have simplicial complexes, which are homeomorphic, they should have the same dimension. But it's actually kind of fussy, isn't it?
I wonder if there's a different way you could do it. More based on the definitions.
Fine linear algebra?
Yeah.
Yeah.
It sort of makes it difficult that, when you, it's called the underlying space, right? Yeah. when you go to the underlying space, you lose some of the data or the original simplexes.
Mm-hmm.
So I guess that's what kind of makes it difficult.
Yeah, if you had a homeomorphism, which like there's a friendly or a homework exercise that could be given here, right? Like if you've got a homeomorphism which like goes face to face, like a face to face homeomorphism, then surely you could probably prove it without this high powered machinery. Yeah. That seems plausible. All right, so next section here, simplicial approximation. And then where we're going in this chapter, of course, then we have abstract simplices, finally simplicial homology. Eventually he gets to the point of talking about the wedges of things, which is interesting construction on page 153. You know, if you have pointed spaces, the wedge of two pointed spaces is the quotient space of their disjoint union in which the base points are identified. So it's like a way of gluing things together in kind of a snazzy way. And then that wedge allows you to create all kinds of new examples. He's got a section entitled Calculations. Ooh, that looks fun. See, eventually he gets to... Oh, where is that stupid thing? I mean, Min talked about this. Sorry. Where'd that go? I was looking through this before class. I was trying to find that somewhere in here buried in these theorems. Maybe this is it. I don't know. Corollary 7.37 on page 172. If X is a connected polyhedron, then... Yeah, this might be. This is a big piece of the puzzle, I think. If X is a connected polyhedron, then the fundamental group of X based at X naught is finitely presented. That is, that the fundamental group has a presentation, with only finitely many generators and finitely many relations. Indeed, if K, H is a triangularization of X, and T is a maximal tree in K, then the fundamental group is simply isomorphic to G of K, T, where that's a thing that's been constructed at this point in the chapter. It's a specific way of combining the data of the triangularization with something called a tree, and the magic of finitely presented groups.
It's not too magical.
No, not too magical.
It might still be the case that the problem of determining whether an element is the identity or not is undecidable.
But I don't know if that actually happens in this application.
Maybe not. That might be another theory.
As you know, these sort of impossibility theorems for presentations have a habit of those worries being not realized for specific examples. You know, I mean, sometimes...
I mean, I think you can actually give an example, though, of a fundamental group of some four-dimensional manifolds.
Mm-hmm.
Like, that's part of the reason why four-dimensional manifolds are difficult, because this undecidability from fundamental group
But
drops
this, I think, the one I'm remembering is a two-dimensional result. It's like, what are the possible... dang it, how does it go? He's somewhere in here, he should have the big theorem, you know? I mean, we pick up the Seifert-Van Kampen theorem later, which is very beautiful. He starts talking about bouquets of two bouquets of circles. A bouquet of circles is a wedge of complexes, where each of the Ki complexes has the form of the boundary of a two-simplex. Bouquet of circles. I love the terminology. Anyway,
One of the examples is a k-fold dunce cap. On page 164.
Dang, I cannot find. Drive me nuts. Just a second, guys. Something I want to say. I can't find the words. Let's go to. Oh man, maybe I don't have it here. Button 2? Yeah, I don't know if it's in button 2. Oh. If I got the right books here. Just like grand glorious result about, you know, possible topologies of two-dimensional things of a particular type, though. I mean, there's still some fine print. That's what I'm not remembering. Oh man, fail. No. I give up for now. I'll find it for next time. Anyway, let's go on there. Oh. Where were we?
Page 136.
136, alright. We will just keep plugging along here. Before you know it, we'll get through it. In due time, of course. But excuse me. Definition. Now we're talking about simplicial approximation. Definition. Let K and L be simplicial complexes. A simplicial map from K to L is a function. Ooh, is this the sort of thing I was just talking about? Phi, which goes from the vert of K to vert L, right? Such that whenever P naught, P1, PQ spans simplex. I think this is what I was talking about, right? Isn't this my face-to-face map?
The underlying map of this is a map between simplices, not topological spaces.
Was your face-to-face map like a homeomorphism? Because this I don't think necessarily is.
Oh, okay. Never mind.
Like if you had this kind of map such that the underlying map was homeomorphism, then I think that's what you're talking about, though.
You have to, like, I guess, need some kind of, like, diagram chasing or something. So, I mean,